On the morning of February 15, 2013, the sky above Chelyabinsk, Russia, was ripped open by a flash of light brighter than the sun. An asteroid, only about 20 meters wide, had slammed into our atmosphere and exploded with the force of around 400 to 500 kilotons of TNT. The shockwave damaged over 7,000 buildings and injured nearly 1,500 people, mostly from flying glass as they rushed to their windows to see what was happening. And the most unsettling part? Nobody saw it coming. It arrived out of the daytime sky, completely hidden in the sun's glare. Now, what if Chelyabinsk was just a little warning shot? NASA and other space agencies estimate there are about 25,000 near-Earth asteroids big enough to wipe out a city. As of today, we've found just over half of them. That means thousands of city killers, each one vastly larger and more powerful than the rock that hit Chelyabinsk, are still out there, completely untracked. So, where are they? Well, the scary truth is that most of them are functionally invisible to us. And the reasons why reveal a terrifying blind spot in our planetary defense. The scale of a hidden threat. To really get the picture, we have to talk about scale. When scientists talk about city killer asteroids, they mean rocks larger than 140 meters across. An object this size wouldn't cause a dinosaur-level extinction, but if it hit a major city, the devastation would be absolute. We have a stunning real-world example of what even a smaller asteroid can do. In 1908, something estimated to be between 50 and 100 meters wide exploded over a remote forest in Tunguska, Siberia. It didn't even hit the ground. The airburst, miles up in the atmosphere, unleashed energy comparable to a large thermonuclear bomb. It flattened over 2,000 square kilometers of forest, an area bigger than London, and knocked over an estimated 80 million trees. If it had arrived just a few hours later, it could have obliterated St. Petersburg. The Tunguska event is the largest impact in recorded history, a stark reminder of the power packed into these small rocks. The Chelyabinsk meteor was tiny by comparison, about the size of a house. The asteroids we're looking for, the thousands of undiscovered city killers, are more like skyscrapers. And right now, they're flying in orbits that cross Earth's path, their individual locations totally unknown. They are needles in the biggest haystack you can imagine, and for a few critical reasons, we're searching for most of them with a blindfold on. Why are they invisible? So why can't we see them? We have powerful telescopes, global networks, and dedicated scientists scanning the skies every single night. The problem isn't just the vastness of space. It's about where and what these asteroids are. The single biggest reason is the sun. Any asteroid that approaches Earth from the daytime sky is completely masked by the glare of our own star. Ground-based telescopes can only work at night, looking out into the darkness. They're effectively blind to anything coming from the sun's direction. This is exactly what happened with the Chelyabinsk meteor. It came at us from the daytime sky, making it impossible for our detection systems to spot. Whole populations of asteroids could be orbiting in the inner solar system, their paths crossing ours, but because they're always lost in the sun's blaze, we just can't find them. The second reason? Many of these asteroids are, literally, darker than coal. They're ancient, carbon-rich rocks that have been drifting in space for billions of years. Their surfaces have an extremely low reflectivity, or albedo, so they barely reflect any sunlight. Trying to spot one of these dark objects against the black of space is like trying to find a piece of charcoal in a dark room with a dim flashlight. Unless it gets very close, it stays a ghost. And finally, there's a sneaky problem of simple physics. For a telescope to find an asteroid, it needs to see it move against the backdrop of faraway stars. But, thanks to a strange geometric quirk, an asteroid approaching from a certain angle can appear almost stationary from our point of view. This slow apparent motion can cause our detection software to just skip right over it. An asteroid that should have been detected weeks ahead might slip through this danger zone and only be noticed hours before it flies by. You put all that together, a massive blind spot near the sun, dark, non-reflective surfaces, and orbital paths that can trick our software, and you get a recipe for a cosmic jump scare. You get thousands of invisible asteroids. The asteroid hunter. For decades, we've been looking for these threats with one hand tied behind our back. But that's all about to change. The solution isn't just a bigger telescope on the ground, it's a whole new way of seeing. The answer is called the Surveyor. Set to launch no earlier than 2027, it is NASA's first space telescope built specifically to hunt for these hazardous objects. It won't orbit Earth. Instead, It will travel about 1.5 million kilometers away to a gravitationally stable spot between the Earth and the Sun called the L1 Lagrange point. From this unique perch, it will have a clear, unobstructed view of our orbital neighborhood. And here's the brilliant part, Surveyor won't be looking for reflected sunlight. It's an infrared telescope, which means it's designed to see heat. Asteroids, even the dark, coal-black ones, are warmed by the sun and glow with their own thermal energy. To an infrared telescope, these dark rocks light up like light bulbs against the cold of space. This completely sidesteps the problem of low reflectivity. Better yet, by being positioned at L1, Surveyor can look back toward Earth's orbit, surveying the very regions of space that are currently hidden in the sun's glare. It's specifically designed to shrink our biggest blind spot. For at least 5 years, the mission will scan the sky, building the most complete map of near-Earth objects ever created. The goal is to finally fulfill a mandate set by the US Congress way back in 2005, find 90% of all near-Earth asteroids 140 meters and larger. With Surveyor, scientists believe we can finally hit that target within a decade of its launch. We'll finally be able to find the invisible. A blueprint for planetary defense, but finding an asteroid is only half the battle. What do we do if we discover one is actually on a collision course? For the first time in human history, we have an answer for that, too. On September 26, 2022, NASA's Double Asteroid Redirection Test, or DART, mission pulled off a plan straight out of science fiction. The half-ton spacecraft, traveling at 22,000 kilometers per hour, slammed head-on into Dimorphos, a small 160-meter asteroid moonlit millions of kilometers from Earth. The mission was a spectacular success. The impact was so effective that it changed Dimorphos's orbit around its parent asteroid by 33 minutes, way more than the minimum goal. DART proved that the kinetic impactor technique is a real, viable strategy for planetary defense. We don't need a Hollywood-style nuclear bomb, we just need to give a threatening asteroid a small, precise nudge, years in advance. Over time, that tiny push adds up to a huge change in position, making the asteroid miss Earth entirely. It's important to remember, though, that DART was a test. A proof of concept. Right now, we do not have a deflector spacecraft sitting on a launch pad, ready to go. DART was a technology demonstration, paving the way for future missions that could be scrambled if we ever find a real threat. The European Space Agency's Hera mission, which launched back in October 2024, is currently on its way to the same asteroid system to study the aftermath of DART's impact in incredible detail, helping us perfect our models for next time. So here's where we are. The threat is absolutely real. There are thousands of city-killer-sized asteroids out there, and most of them are still undiscovered, hiding in the sun's glare or just too dark to see. Events like Chelyabinsk and Tunguska aren't theories, they're documented reminders of the raw power these things carry. But for the first time ever, we're on the verge of having a complete system to deal with this danger. The Surveyor will give us the eyes to find the hidden asteroids. And DART has given us the blueprint for a shield. We have proven that with enough warning, we can protect ourselves. Human ingenuity has given us a path to safety. The question isn't whether we can do it anymore. It's will we? The next decade is critical. It will take sustained investment and international cooperation to build these test missions into a real, operational planetary defense network. We've gone from being passive targets in a cosmic shooting gallery to active defenders of our own planet. It's a profound shift in our place in the universe. But this new power isn't guaranteed. It depends on us staying focused and funding projects like Surveyor and future deflection missions. So I have a question for you. Do you think building a full-scale planetary defense system should be a global priority? Let me know your thoughts in the comments below. And if you found this look at our planet's hidden threats and the amazing tech we're building to stop them fascinating, think about subscribing and hitting that notification bell. We've got many more deep dives into the future of science and humanity coming your way. Thanks for watching.